Subscribe now.
You are welcome to today's tutorial. In my previous tutorial, we learned how to calculate 4-point DFT and also 2-point DFT with some examples. And now we are transitioning to the linear transformation method. So up till now, we have been calculating discrete Fourier transform, which is DFT, using the direct computation as usual, as the direct computation method. And this direct computation method involves most explicitly summing the product of the input sequence with a complex exponential, and the complex exponential that we were using, it's exponent negative j 2 pi over n nk. This is the complex exponential that we are using, and we were summing them up together with the product of the input sequence with those complex exponential function, which is this one. So now, while this method is conceptually straightforward, sometimes it can become most of the time it can become computationally intensive for larger discrete Fourier transform sizes. For example, when you are doing n equal to 2, that is the sequence x of n, which is maybe 1, 1, it is easy to compute because it doesn't consume much time. When you have n equal to 4, for example, we have x of n equal to 1, 2, 3, 4. Though it's easy to compute, but actually it wastes a lot of time. So as you can see, the difficulty nature or the time-consuming nature of this question comes into play when the size of the sequence is increasing. So imagine you have 8 points DFT, you have 16 points DFT, which is n equal to 16. Are you going to use the direct computation, and what is the time that you are going to use to compute all the 16? Right, this is a bit time consuming. So based on that, to overcome this limitation that I've mentioned here, we can use more efficient approach, which is known as the linear transformation method, also referred to as the Twiddle factor method. Right, the Twiddle factor method or the phase factor method. This method leverages the property of symmetry in the digital or the discrete Fourier transform to reduce the number of complex multiplication required. So basically, the key idea behind this linear transformation method is to decompose the discrete Fourier transform calculation into smaller DFTs of size of 2, and based on that, we can compute that to achieve whatever we want to achieve by the use of the periodicity and the symmetric property of this complex exponential term in the DFT formula that I showed to you earlier on. So basically, by using the linear transformation method, we can significantly reduce the number of complex addition as well. So in the next tutorial that I'll be doing, we will go through some sort of examples of calculating the 4-point DFT using the linear transformation method to kind of demonstrate its efficiency and effectiveness as compared to the direct computation method that we have done. So yeah, so as I said, the linear transformation method, let's kind of derive something small here. X of k is equal to summation of n equal to 0, n minus 1, x of n, exponent j 2 pi over n nk, where k is equal to 0, 1, 2, and then n minus 1, right? So based on this, looking at whatever you are seeing here, we are using omega n to be equal to exponent negative j 2 pi over n. And this method, this particular exponential function term, is what we call the Twiddle factor. The Twiddle factor. This exponential term out of the total term of this is what we call the Twiddle factor. So based on that, I can rewrite the general equation, which is this, into a simpler form as s of k equal to exponent n equal to 0, n minus 1, x of n, And then instead of writing this exponential whole term here, I'll write omega n and then nk, because this one represents this. So since I have this here, this small n means that if you are computing 8-point DFT, that means that the Twiddle factor is of 8 points, so 8 will be replaced over here. That's how it looks like. It's nothing over there. So now that I've written this one here, we can use this Twiddle factor method to kind of generate something here. Let's proceed and see what we can do. Now, for a 2-point DFT, of which we are going to get n equal to 2, we can write the formula as x of k to be equal to the summation of n equal to 0 to 1, and then x of n, and then the Twiddle factor aspect is omega 2 n of k. And you have to take note that k is equal to 0 and 1, right? K is equal to 0 and 1. And since k is equal to 0 and 1, when we are using direct computation, it's going to be for k equal to 0, we're going to x of 0 to be equal to the summation of n equal to 0 and then 1. And then as we know already, x of what? N is going to be Twiddle factor. If going to Twiddle factor 0, right, that k is equal to 0, so whatever we do, the exponent is going to be 0, right? And then based on that, we can simplify it as x of 0 of 2 of 0, right, plus x of 1 of 2 of 0. Remember that when we were doing the direct computation, we were doing something like x of 0 exponent 0 plus x of 1 exponent 0 for the first element. So this is what is manifesting here. Yeah. So based on that, we can rewrite our final version as x of 0 to be equal to x of 0 omega w2 0 plus x of 1 w2 0 for the first element. So we can name it our equation 1. So looking at the second element, which is k equal to 1, we are going to get something like x of 1 to be equal to exponent n equal to what? 0 and then 1. But remember that the first element for n is 0, right? So if the first element for n is 0, so when n multiplied by k is going to give us 0. So we are going to get x of 0 multiplying by what? 0. So this is the Twiddle factor over there. And then we are going to get something plus x of 1. X of 1, remember that n equal to 1 and k is also 1. So if n equal to 1 and k is also 1, we are going to get the exponent of the w to be 1, and then here is 2. Right. So this is how we have what we have over here, and in all we can rewrite it as summation of n equal to 0, 1, x of n, omega 2 power n, right? Which can also be written as x of 0 based on whatever I've done here, omega 2 power 0 plus x of 1 omega 2 power 1. Yeah. So based on this, we can come out with our final equation as x of 1 to be equal to x of 0 omega 2 power 0 plus x of what? 1, and then omega 2 power 1. And this is going to be our equation 2. So based on this, I hope we all did linear algebra. So for in the terms of linear algebra, if you have two equations like this, you can form a linear combination out of it, right? You can use the linear combination out of it to form a matrix. And based on that, if you want to do that, we have the input to be x of 0, output to be x of 0, and then x of 1. So that one is our output. So x of 0 and then x of 1 is going here. So if you did linear combination, you will get to know what I'm trying to do over here. So now x of 0, x of 1 is our output here. Now it's equal to, so based on these two equations, right, we want the x component to be able to multiply it in such a way that when we multiply everything back, we will get the original equations back. So therefore, I will say that we are forming a linear combination out of it. So since we are forming a linear combination out of it, the coefficient of the x values inside can be extracted out. So the first one, we are having x of 0 and x of 1 with the coefficient of them to be omega 2 0 and omega 2 0, right? Omega 2, that's x1, so we can name here as, let's say, x1 and then x2, right? So omega 2 0 and then x2 is omega 2 0. So we are forming the linear combination. And then the next one is omega 2 0 and then omega 2 1. So we are going to get omega 2 0 and omega 2 1. So this is what we have now. And then we need to multiply by the input, which is of x of what 0 and x of what 1. The way I've been writing the x, maybe you may be confused, but you can also decide to do this one capital X rather, because we are dealing with the frequency capital X so that you will not be confused. And here will be small x. So now you can see that if I want my capital X of 0 is equal to, you know, the multiplication of matrix, row and column. So here, let's say if we had x1 and x2, we are going to get omega 2 0 plus omega 2 0 x of 0, right? And then plus omega 2 0 x of what 1. And this is x of 0, sorry, x of 1. And this is the same equation that we have gotten here. This is it. And when we want to also expand this one multiplied by, so we are going to get x of 1 to be equal to omega 2 of 0 x of 0 plus omega 2 of 1 x of 1. And this is also the same equation that we got here. So this is basically a linear combination out of the equation that we got. So now, since we have this equation, we will draw the Cartesian plane, the complex number plane, right? So for the complex number plane, the vertical axis represents the imaginary axis, which is what? Negative j and j. And then the horizontal axis represents the real number axis, which can also be written as 1 and negative 1. And looking at our previous calculation in my previous tutorial, anytime that you see exponent of 0 is given as a value of 1, right? And anytime that you see exponent of 1, right, also give us a value of negative 1. You get me? Negative 1 for the part in which exponent can be either negative j pi on 2 and the others, right? So based on this, since for this matrix we are having omega 2 of 0 and omega 2 of 1, that means we have only the real number axis in use, and therefore we can say that our omega 2 of 0 will be here, and then omega 2 of 1 will also be this side, right? In the case whereby you get a higher exponent, it means that the imaginary axis can also be included. So looking at this, you can also use your calculator to confirm for a 2-point, because this is actually a 2-point DFT, right? For a 2-point DFT, exponent negative j 2 pi on what 2 nk, right? And then if you are doing this, let's say we are doing for only the Twiddle factor here, because this one I've already sorted it out. So this one will cancel this. Exponent negative j pi will give us what? Negative 1. But if this one is 0, it will give us 0 and we are going to get 1. You can also use a calculator to confirm for this. So based on that, we can rewrite this matrix equation that we have come up with as x of 0, right, and then x of 1, and this is going to give us, because here it's 0 0 0 0 and then 0 1, we are going to get 1 1 and then 1 negative 1, as I've indicated here, or you can use calculator to also confirm here. So based on this one, we are multiplying it by what? X of 0 x of 1. So this is it, x of 0 x of 1. And now that we have this, we have been able to come up with a linear combination involving the matrix of a 2-point DFT, right? Of a 2-point DFT. So in my next tutorial, I'm going to also derive or talk about how we can derive the linear combination of a 4-point DFT using the general formula as well. So thank you for watching and have a good day.